Hello and welcome. In this video, we're going to be looking at JavaScript binary searches. And in previous videos, we looked at recursive functions and specifically the Fibonacci sequence. And in that video, we looked at a Fibonacci sequence finding the value at an index position. We did it in a loop and we did it through recursive functions. And what I want to do is give you another example of sort of uh, a, a a time sensitive algorithm. And what I mean by that is in the previous video, we looked at those two, recursive versus loop, and generating that Fibonacci sequence or solving that Fibonacci sequence. And one was faster than the other. And what I want to do is before we cover judging algorithm speed or efficiency, I want to show you just one more algorithm. There's a lot of different searches that are available, but the binary search is a good one because it shows us just um, a different time and space complexity that we can compare to the recursive functions and in the video that we're going to do on algorithm efficiency. So, a binary search. Well, let's just talk about searches in general. Computers are great for searching through things, right? Finding an item on a list. Well, kind of. So, let's start off with a problem. Okay, we have a list of students, and we want to know if the last name of Smith is on that list of students. What are our options for searching through that list? Well, we could, or think of it as like a stack of papers. If you wanted to check if you're a teacher and you want to check to see if a student passed something in a stack of papers, right? Where would you start searching through that stack of papers? Well, you have two options here, I guess. You have many options, but we'll give you two. You search through the list one by one. You go through the stack of papers and you search through every single student until you find if the student Smith submitted their work or if the student was on the list. Okay, that's one method. The other method, option B here, is we split the lists, split the stack, and we only search through the half that is likely to contain the name. Which one is going to be faster? You're probably thinking, well, why wouldn't we just split the stack? If only half is likely to contain the name, say there's 30 worksheets, 30 students, why wouldn't we split the stack and then we only have to search through 15 students? Okay? That is true. And that is something that, in this case, would be faster if the list is sorted. If you have a sorted list where it's alphabetical, let's say, then yes, it makes sense to split the stack and only search through 15 of them if there's 30 students. But if the list is not sorted, then going through one by one is going to be maybe your only choice. But for today, what we're going to do is we're going to assume that the list is sorted. And in that case, if the list is sorted alphabetically or numerically, say starting from 0 to 100, right? It's sorted in some sort of logical way. If that's the case, then splitting the list is going to be faster than going through the entire list one by one. Okay, so the splitting of the list, that's called a binary search. And given a list of items, say names or numbers, what we can do is we can use a binary search to search through that list of items. What it does is it finds the midpoint between the two endpoint values. And in the case of Smith, it might start with A and Z for their last names. And it will find the midpoint between the two. Okay. So it would be the letter 13, which is M. So it goes through A to Z, finds M, and then it would say, okay, which side or which pile or which half is S likely to appear in. And so then it will go and find that second half. It'll go through, find the midpoint between the remaining 13 letters. We can round up or round down depending. And then we search through that, and then we search through it again, and we break it down more and more. Okay. Say, for instance, we are searching for a number. And we're searching through a number. We have 1 through 71 here. And in this case, these numbers are sorted, but there's some numbers missing. That doesn't matter. Okay. because what we'll be doing is searching through the index position. So even if you had a class starting with Smith, or you're looking for Smith in a class of students, it doesn't matter if there's students that don't have the last name that starts with L or something. You could just can take the list of what's available, find the midpoint, and then go either to one half or the other. So in this case, if our target is 7, if we're looking to see if this list of numbers contains the number 7, okay, we can, assuming that the list is already sorted, so this is not a sorting algorithm, we have to assume that this list is already sorted by something else, either it comes in as sorted or it's sorted previous to this step. This is a searching algorithm. So what it's going to do is it says splits the list. So we have index position 0, index position 16. It splits the two. We get index position 8, so that's where it starts its search. It says, okay, is 7 less than 14 or greater than 14? Less than 14. So now it shifts to the left and creates 2 new endpoints. It will go to, so 14 divided by 2 is going to be 7. We have a new endpoint of 6 and 8 as our min and max numbers, and we find the midpoint of that. It's going to be 7. To show you another way, something like this. If our target number was 4, then we would take the min number, which is 1, or 0, actually, and the max number of, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I don't want to make sure I wasn't miscounting here. 0 to 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, all right, never mind. So we get index position 0 to index position 8. Yeah, so for 9 letters altogether. Okay, so all right, so it has 8 letters altogether. So it will set the midpoint, 9 numbers altogether. It sets the midpoint between them. So that would be right here. And then it will say, is 4 less than 7? Yes, it is. So it eliminates this half. So now we have a new midpoint, which will be 4. And a new, is 4 greater than or less than 3? It's greater than. So now it shifts to the right. And now it does a midpoint of the remaining numbers. And it will eventually get to 4. So essentially a binary search, we can think of binary as just simply asking the question, is the thing you're looking for greater than or less than the items to its left and right? And if it's greater than or less than to the items to its left and right, okay, depending on what the answer is to that, it'll either shift the search to the left or shift to the right and search those remaining values on and on until you get until you find your answer, until the answer where the midpoint essentially matches the number you were looking for. This is a very efficient way to look at a list of items and to find an item in that list, or determine if the list is there or not, or if the item is there or not. So we can go over the pseudocode for it. So this would be implemented in any language. We're going to do it here in JavaScript. But what we do is we initialize 2 variables. Min is going to give just 1, or actually, depending on min, it might be 0 here. We could do 0, I guess. I don't know why I wrote 1. That should be 0. There we go. So, okay, let min equal 0. And then max is, the max value is going to be the list length minus 1. So if there are, like we showed you in the other one here, if you have 9 items, okay, the max index position value would be 9 minus 1, so 8, because 0 is going to count as an index position, because JavaScript indexes at 0, just like practically every other language on the planet. Okay, so yeah, we have the min is 0, and then the max will be the list length minus 1. And while the min is less than or equal to the max, basically continue. If it's not, we stop the program immediately. This operates as like a century. Then we get the midpoint between the max and min values. We round it down so it becomes an integer. If the midpoint is the target number, we stop the program. But if the midpoint is too low, we set the min to be the midpoint. Let's see, midpoint. Did I mix this up? No, that's right. If the midpoint was too low, right, we set the minimum value to be the midpoint plus 1. So the midpoint is not it, it's too low. So we have to increase that min value to now the number that's immediately to the right of the midpoint. And then if the midpoint was too high, we know that the midpoint is currently not the target we're looking for, and we know it's too high. So therefore, we have to drop the max down to narrow down that range. So we drop it to the value that's one less than the current midpoint. And then we set it in a loop. So we go back to step 2 and we do a check. Is it less than or equal to the max? Continue. And then if the target is non-list, basically at some point you will reach a point where the min is not less than or equal to the max. It'd be greater than or equal to the max. Then at that point, you know that the this handles the less than or equal to will handle if there's only 2 things in the list. But we have to make sure that as this program runs, it will set the min to be +1, and if the min is greater than the max, we know that the program has stopped or should stop. And in that case, we just return back to the user that did the program that the return was unsuccessful. That whatever we're looking for is not in that list. Okay, so we'll actually go through and actually write this all out in JavaScript. And just one little quick, I can show you this pseudocode, how it's going to run. A neat little animation here from penji.com. Thank you, Penji. Okay, and just going through and searching in binary, right? So binary is 2 options. Binary search tree, it will determine this, and then it will go to 25 and determine is it greater than or less than 27. It goes here. And in this case, I don't think there's any number here. Yeah, there is not any. That is a point where there's only 2 things on the list, which actually brings up another good point about this. That you can do a binary search tree, but the smaller the list, it actually becomes a little more efficient to just do a linear search. So if you only had like 4 items on a list, just put it in a loop and just go through all 4 items at once. That it would be more computationally expensive to go and actually implement a binary search tree. But the longer the list gets, and we'll show you this in a future lesson about algorithm efficiency and how we measure that and judge that. The longer the more items you have to compare, or the more items in the array or the list, is the greater the cost of a linear search is going to be, and therefore a binary search tree is going to quickly pick up in efficiency as the list grows bigger and bigger. It's a very, very efficient, very good algorithm for searching for anything. As long as the list is sorted, that's the trick. As long as the array is sorted, if it's sorted, use it. If it's not, don't use it. It's gonna mess up and you're not gonna find your items in your list. It's gonna search through the wrong half. Okay. All right. So let's write this thing out and see what this would look like in JavaScript. All right. So we're gonna start with say we're going to search a list of items for a prime number. And calculating if a number is prime is actually really computationally expensive. So what we'll do is we'll just provide a list that I had ready of constant of primes. So 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37. So basically all the prime numbers from 0 to 100. Okay, and basically what we want to do is search through this array and find out if a number is in here to see if it's prime or not. So what are our options for writing this? Well, we could do a for loop, right? And the for loop is an option, but it maybe isn't the best option for this exercise. Not on its own anyway. Because we'll be dealing with testing for different prime numbers, we're going to start off by wrapping this whole thing in a function. And for our function, let's just call it binary search. And for our binary search, we'll take in 2 different parameters. Let's take in the array we're going to be searching through and the target num. Obviously, if you're not searching through numbers, then target num you might want to rewrite into like just target. But I'll do target num to make it clear. All right, and then going up here, we said let min equal 0 and let max equal list length -1. So let's do that. Let's min equal 0 and let max equal array.length -1. Because in JavaScript, we're not going to be looping this function. We're going to be modifying or mutating these variables as we go. We'll set them as lets so we can change those instead of consts, just so our program doesn't crash. Okay, so now we get to the actual loop part where we're going to go over, essentially we need to go through each element in the array at some point. Well, actually not, we don't need to go through each element in the array. We're not doing a linear search. But we're going to be jumping to the midpoint, and we're going to need to jump around a bit here. So for a loop, we have two options. In JavaScript, we have a for loop and we have a while loop. And a for loop is just given the items in the list. You know, going through with a for loop could be kind of hard because a for loop is great for going through almost like linearly. It goes through and each item in the array, it does something too. We'd have to check each position in the array to find out if it meets certain conditions and then go to the next one and then loop back through. A for loop could be kind of tricky just because it doesn't go in sequential order. So in that case, like I said, a for loop does great in sequential order, but in this case, probably not. So a while loop is probably the better choice with this one because we're going to be jumping around and we're essentially just looking to check for a target. So we can set up a while loop. And we set up here that while the min is less than or equal to the max, we can run our code. And the next point is if get the midpoint between the min and max values. Because this will be in a loop, we can use const. It'll be scoped to just this loop and reset once we run the loop again. We can use the JavaScript math.floor to round down. And in that case, we're going to do min plus max. We'll get an average between the two, divided by 2. So this will round it down, so we get the min plus max divided by 2. So if we have 100 items on the list, we would start with 0, go to 100, divide by 2, start with the 50th, whatever's in the 50th index position. So we have const mid, okay? And then we can do the next part of if the midpoint is the target number, stop. So we're running a function. To stop it, we'll use a return. If array mid, if the midpoint of the array is equal to the target num, basically if the index position, if the value at the mid index position is the thing we're looking for, we need to stop the program. And in that case, we can just do return. We'll just return that, that value, okay? Or we'll return the index position of that value. We know what we're looking for, so it's not that we don't need it to tell us array mid, because this would just report out what's ever in the value of that index position. We already know what we're looking for. That's what we entered in when we said target num. So we just want to know what position, where it is in the array. We could say just like return true or something, but it'd be kind of interesting just to see where it actually is in the array. Okay, so if this is true when we run our program, then the program will stop immediately when we get to array. We could structure this as like if else statements, but I'm gonna show you. I'm gonna do a sequential if statements just so you can see this whole algorithm written out. So if the midpoint was too low, set the midpoint plus 1. Okay, if array dot or mid the is less than target num. So if the value at the midpoint position is lower than target num, so let's say if we're searching the 100 items and we're looking for, is 25 there, we go to the midpoint, which is 50, and we determine that, actually, we'll say the target's 75. We determine that 50 is less than 75, so we need to bump it up. Let's do that. Min equals mid plus 1. Okay, that handles that. And now we can handle what happens if it's greater than. We don't need to pass in a condition check for this because it's just simply going to be the only other option, right? So initially the program will stop if we run into, if we get lucky and the first thing we search or whatever we search is that target number. And then if it's too low, go higher on the min, else max equals mid minus 1. and that will drop it down. Midpoint was too high, set the max to be midpoint -1. Okay, and let's see. So then, all right. So then let's go and let's do a test run of this thing. Let's set up so this is going to return the array. And so this is going to return a value. So let's set up a variable here, say const result is going to equal binary search. We'll do primes as our array, and then we pass in a variable or a value that we want to find. Let's just assume that it's there. Let's do 5. Let's search to see if 5 is there. Okay. And let's do console.log prime number found at index position. And then I'm doing this as a template literal. So make sure that you use the backtick next to the 1 on my keyboard instead of this is not a that's not a single quote. Okay, index position, and then we'll pass in the variable result. Prime number found at index position. Okay, there we go. And everything looks good. Position, yeah, okay, let's run it. All right, prime number found at index position undefined. Const results, result. No, that's right. So let's console.log binary search primes. Results not defined. That's fine. So it's still returning undefined. Okay. Let's go up here and I did array mid. There we go. When I was showing you earlier, I erased the wrong thing. So we return mid. Still undefined. What? That's wacky. Ow. Whoops. I know what I did. The while loop should be max is greater than min. Why would I reverse that? Doesn't make any sense. All right, now let's run it. There we go. All right, so let's go back and restore my original constant result variable with binary search. There we go. Here. Okay, good. Prime number found at index position 2. So, all right, interesting. Why was it returning undefined if you didn't pick that up? It was returning undefined because the whole function was undefined and we were console logging the function, which brings up another point. So the while loop essentially was never running because I had accidentally reversed my max and min positions. I don't know. So it brings up another question here is what happens if the number is not there? So let's give it 1. Okay, prime number found at index position undefined. So we have to do something to handle the case of what happens when the number is not a prime number, not in our list. So what I'll do is we could do it anywhere in here. I'm going to, because this is a function and I essentially want to return a value to it. We want to basically console log something if this while loop does not run at all. So in that case, what I'll do is I'll just go right down here and our algorithm says, or pseudocode says to, if the target's not in the list, return unsuccessful. So we could send back a string as a message, but I'm just going to return false for right now. That essentially it's not there. You could return null or undefined and do a check for it. I just like false because it's not true. It's not there. Prime number found at index position false. Okay, so we can actually clean this up a little bit. We can do so we run the test here if result, and we can do if result, and then we can move that up. And I'm just going to change my spacing on that so you can see it. Else, and we can do console.log. This one I'm going to use regular single quotes. That is not a prime number. Okay, so what I do here, if result, remember this is the same thing as saying is true. So if result is true, basically if there is a result at all, It doesn't matter what the result is or what it comes back as. Basically, does this return something that's not undefined or null? So we can shorthand it just to do if result, if that's true, if there's something there, say what we planned on, and then else that's not a prime number. Okay, so we see it runs. That's not a prime number. We can do a test for a couple different things here. Actually, I'll do let for result for this, and then I'm going to take this. I'm going to copy it to right below it, and let's do a test for 13. I have to get rid of the second let statement, otherwise it's going to yell at us. Prime number found at index position number 5. Okay. And then we see it actually returning very quickly. Like I said, there's a very efficient algorithm. Let's do one more. 13, and let's change this to 17. Found at index position 6. So it's searching through here, it's finding our target, and it's returning that back to us. And would it be faster to go through a linear search for each item on the list, check to see if it's the value num? I mean, yeah. I mean, this is not that long of a list, and how many items on a list does it take to get more efficient? It depends on a number of different things. I mean, what we can do is I'm going to show you next time is what's called benchmarks, and we can enter in different array lengths to determine when it becomes more efficient. Or I could just show you a chart to show you. But one thing we can know is how many times. Here's another question that we don't know yet. It doesn't tell us is how many times does this loop need to run in order for it to find that item. So let's check this out. Let's set up a new variable at the top here. And let's do let counter equals 0. And what I want to do is every time this loop runs, let's increment counter by 1. And actually for this, I think I'm going to turn mid, turn false. We can either make it global or just console log it inside here. Let's just keep it inside the binary search. Okay, so let counter equals 0, and then after each run, let's add counter plus equals 1. Let's add 1 to counter, and then let's add a console log statement at the end of this thing. So we could do we have to do it before the return statement, because as soon as you reach the return statement, the program stops running. So console.log, and we'll enter another template literal. Let's do let's say the number of items searched, and let's add in the sign. Let's add in that counter variable, and I'm going to add this right before return mid as well too. Like I said, we could make this global and just do it once at the bottom there, but okay. Let's see. Oh, because we ran it twice here. Let's run it just once. And let's just do up here, let result. Now I have to keep on changing this thing. We can just do results. Then we just reassign result to the returned value of binary search. Let's comment those out and run it one more time. Number of items searched. Okay, so we looked for 1. We find the number of items searched was 4. Essentially, how many times did this loop need to run until we found the midpoint equals the target num? Let's run the next line here. And that's 13. Okay, number of times the item is searched, 2. That's pretty cool. Let's do the next one, 17. Okay, number of items searched through 4. Prime number found at position 6. Let's enter in a number that's a little bit higher. Let's enter a number that's above our search list. So let's do 79. And I'll comment this other one out here. Move that all down. Okay, number of times the item searched, 3. Prime number found at index position 21. So we're getting what, between 3 and 4 3 and 6, 3 and 4. Let's see. Okay, so we got between 2 and 4 times that needed to search the items to do it. Now let's compare that to a linear search. So let's enter 97. Let's do the maximum result. Comment those out. Comment that one out too. Actually, I'll just do 97 here. 97. Is that the last item on our list? That's the last item on our list. That's the last prime number on our list. Okay, number of items searched, 5. So, and prime number found at index position 24. So the last item on our list, essentially. And we look at this and we compare this to a linear search. If we were in a for loop on this and compared each item in the array to the target we're looking for, how many things would it need to search through in order to find out if 97 is inside that list? If the thing at the index position 24 or 21 or whatever the index position 0 to 24 searches through every index position to see if that item is there. And remember, computers can't see these values. The computer doesn't care what these values are. It's not like it can look at the screen like you can and say, "Oh, 61, it's right there." Humans are good at that. Computers are not. So computers, if we do a linear search, computers have to go through each one and check for something. In this case, we're just checking to see if the thing in the first position is the number we're looking for. So how many times would it need to run through the entire array to find out if 97 is in that list? Just true or false. Well, this is in the 24th position, so it's going to have to search through 24 different items or 24 different comparisons to test if that item is there or not. Versus when we did a binary search, we found out that it only took 5 comparisons to find that out. Now, obviously, if we have a short list, okay, let's just say we're going to search through 97, and let's get rid of, I'm going to cut out everything between 89 and 97. So we have only 2 items in our array of primes. And let's run it again. Okay. And we could see the number of searched items is 2. We compared both of them and found the prime number position 1, right? So it goes, where are we? 0, 1. So a linear search, would a linear search have to, comparing each item in the list one by one? Would that be faster or slower? Well, it's going to be the exact same, right? Items in the search, you have to search through 2 items in a linear search to find this out. So I said earlier in this video, when we first started out, that when we start off with our original question, a list of students checking to see if it contains the last name of Smith. Is that going to be faster just searching through the list one by one? Or is it going to be faster splitting the list and searching through the half that's likely to contain the value? Well, if the list is sorted, and I'm going to show you this right now. If the list is sorted, okay, we reverse the numbers here. All right, what happens now? What's it going to think now? Okay. Number of items is searched is 5, and that number is not a prime number. So we searched for our 97. 97 is in the list. It's the second thing, but our list is not sorted. And so it does what it's meant to do. It goes through the list, compares the max and min, and it compared the 2 of them and realized that, whoa, the min number over here is 89 and the max number is 83, and those should be reversed, and I don't know what's going on. So we're just going to exit the program, right? That's our century to make sure the program stops when we want it to stop. So it returns false. That if you have an unsorted list, this could happen. What if Smith is the second one, but the first one, like first last name starts with Z? Then the whole thing is going to get messed up. The computer's not going to know what's going on, and it will return that it's not there when it is there. So a sorted list, linear search is going to be slower the bigger the list is, and it's going to need more comparisons. And a binary search is going to be faster on a sorted array, sorted list, the bigger it gets. Okay, and if it's unsorted, then you get a big problem. All right. So then you have to sort. You either have to sort the list, or you have to perform a linear search on it to go through each item one by one to find out if the item is there or not. And sorting is going to be a whole nother algorithm that is going to require time. So which one is faster largely depends on how many operations do you need to perform on an item or on a list in order to basically accomplish your goal, or to solve your problem. So here I wanted to take you through just a binary search, because this is a classic example of a type of speed or type of algorithmic speed or calculation time that's logarithmic. And last time we looked at the Fibonacci sequence, that was a recursive function, and recursive functions are factorial, and those are going to be a lot more computation expensive. In the next video, we're going to take a look at those different calculation times and how can you judge whether an algorithm is efficient or inefficient. If it takes up, is it better to write it one way or another way? This is stuff that you don't really focus on as a beginner, but it's important to know as you go forward in your skill set to write out a program and then say, oh, I can rewrite this and make it a little bit faster by rearranging this or maybe using a binary search on it to increase the speed. And why is increasing speed valuable? Well, time is valuable, right? If you have a program that's going to take a lot of calculation time, if it's going to take 10 minutes, well, 10 minutes is going to cost, electricity, right? So if you have a computer at home, it's going to cost you your electricity. But if you have a cloud computer, right, or a cloud service, calculation cost is charged by the minute or by the number of calculations that are performed. So if you can reduce all that, that has a real monetary value. It has a real savings that you're going to be accomplishing by making your programs more efficient. And it's going to save you the time of having to wait for the results to come back. So that's it for this video. We'll take a look at speed and calculation speed in the next one.